and exponential functions. So 3.1 polynomials and exponential functions. Okay, so let's talk about what is called the power rule. The power rule has multiple angles if you want, but we're going to look at the simplest possible form right now. So x to the nth power, any power, including negative, which is really not a polynomial. If the power is -5, this is no longer a polynomial. But the rule is the same. So when we want to differentiate this, all we have to do is bring down the power and multiply by x, and we subtract 1 from the power. So this is the power rule. What I should multiply by, really, is by x prime. But x prime is the slope, so it's not, I don't want to write the equal symbol. I want us to determine the slope of x. Can anyone give us the slope of x? If I have y equals x, what is the slope of this line? It's a linear function.
1.
Yes, the slope is 1. So this really tells us that, as we know, the derivative is the slope of the tangent line to the graph at any point. So keeping in mind that moving forward that x prime is 1. So we really, but keep this in mind, I'm going to sort of delete it from here because it's 1. But later on I will get to something else and then I'll have to put it back in. So I would like us to get used to it from the get-go. So the power rule, one more time, says n and subtract 1 from the power. Okay. I would like to discuss the square root of x. But although we know that this is the derivative of the square root of x, we know that this is not a polynomial. But this can be rewritten as x to 1/2. I hope everyone agrees with this. And I will have to use the exact same rule. I bring down 1/2, I copy x, I subtract 1 from the power, and I get -1/2 because 1/2 minus 1 is -1/2. If you remember from algebra, we don't like negative exponents, so in the numerator or in the final answer. So I will write 2 to x to 1/2, but that is nothing else but the square root of x. So this is our, if you like, third rule so far. The derivative of x is 1. The power rule is n times x to n minus 1 times this prime, but that's 1. And one more rule that I'd like to add moving forward is that the square root of x prime is 1/2 the square root of x. And yes, I should write here, I'm going to erase it for now, I should write times that inner function prime. The reason why I will erase it is because it's 1. Okay, so with what we have so far, I'd like to look at a few examples. Please choose if you'd like, if not, I will. So, just a couple of examples. For example, this y equals x to 5/3 minus x to 2/3. We're asked to find y prime or f prime of x if I denote this by f of x, but they are the same always. The other notation is the derivative of y with respect to x, the derivative of y with respect to x. Another notation could be d over dx of the function f of x. What's with all these notations? Why do I need to have, well, sometimes you're going to see it like this, other times like this, other times like this, other times like this. I just want you to see that the first derivative can have different notations. This is called the Leibniz notation, as well as this. So it's the derivative of f of x with respect to x, or the derivative of x or the derivative of y. Okay, so I'm coming back to y prime if you want. So when I differentiate this side like it's a power, I apply the power rule. I bring down 5/3. I copy x. For now I'm going to write 5/3 minus 1, but we should be able to calculate that without writing it, but it's okay if we do. Minus, I bring down the power 2/3 and x to 2/3 minus 1. I hope no one has difficulties with fractions, with operations with fractions. So this is minus 1. The least common denominator is 3. So this one needs to be multiplied at the top by 3. So 5 minus 3 is 2. Same thing. 2/3 minus 1. The least common denominator is 3. This has to be multiplied by 3. 2 minus 3 is negative 1. Also written with minus in front, 1/3. So I have to go back and continue here. So then finally y prime is 5/3 x to 2/3 minus 2/3 x to negative 1/3, or maybe I should write it so everyone will see that. So we prefer, you can leave it like this. For this particular function, right now, you can leave it as is. But what if we don't? If we don't, I will have to write this, the cube root of x. So this is the multiplication, so it's not, so it's clear to you. Any questions so far? Any questions so far? The other thing that I would like to mention is, which we already used, if a constant is multiplied by a function, any function, and we differentiate this, so this is a factor. This will be c times f prime. What if we have a product like h of x equals x minus 2 times 2x plus 3? At this stage, we do not know how to differentiate a product. This is a product of a function f of x multiplied by a function g of x. We do not know how to differentiate a product yet. We will, hopefully today. So since I don't know how to differentiate a product, that's no problem. I will distribute. So x times 2x, 2x squared, x times 3, positive 3x, negative 2 times 2x, negative 4x, and negative 2 times 3 is negative 6. So far, I have the simplified form of this function as 2x squared. Just want to push this computer further. Okay. So I simplify the function, removing parentheses, combining like terms. I have 2x squared and minus x and minus 6. And now I can differentiate. When I differentiate 2x squared, I bring 2 in front, and I have to multiply it by 2 because 2 becomes a factor. So 2 times 2 will be 4x. And the derivative of x is 1, but I have negative here. It's a constant times x. So this is the derivative of this function. So we should write, just to refresh our memory on what this means. This function gives the slope of the tangent line to the graph of h of x at any point where the function h of x is, and I'm waiting for you to give me the correct word that I'm missing here.
Continuous?
Careful. Not all continuous functions have derivatives.
Differentiable?
Yes!
Differentiable.
Yes. It happens it's a linear function, a quadratic. They will always be differentiable. You will always have a derivative. But not all functions will have a derivative everywhere. We know the cusp, the corners, a vertical tangent. So this function will give us the slope of the tangent line. Also, not just the slope of the tangent line, but two other things. Or, I'm going to write or. So the slope of the tangent line or the instantaneous rate of change. Or the instantaneous velocity. Depending on what the function is all about. So the rate of change or the slope of the tangent mean exactly the same thing. And the instantaneous velocity makes sense only if the original function is the distance. So I can put in parentheses if h of x is the distance function. If it is the distant function, we can talk about the slope of the tangent, but at the same time we can talk about the instantaneous velocity. And almost no one had difficulties with, but some of you did not address that issue, so I'm going to select a problem. For example, let's say we have a function that is y equals x to the fourth plus 2x squared minus x, and we are given the point 1, 2. Find an equation of the tangent line to the curve at the given point. Find the equation of the tangent line at 1, 2. So I want to determine that. Now it's easier because we don't have to use the formal definition of the derivative function. I'm just going to refresh our memory on how it looks like. So remember f prime of x, there is only one definition, the limit of the difference quotient. So f prime of x is the limit of the difference quotient, which is the same with limit as h approaches 0. I don't want you to forget this because this is very important. X plus h minus f of x over h. No, we are not moving forward. We are not going to use this. We are going to use the differentiation rules. So for this problem, I will immediately find y prime. Can anyone give us y prime for this function? For x to the fourth plus 2x squared minus x.
That'd be 4x cubed plus
Yes.
4x.
Yes. Yes. Excellent. 4x to the third plus 4x and minus 1. Now, if I denote this by f prime, that's very nice and easy. I'm going to determine this. 4 plus 4 is 8. 8 minus 1 is 7. If you don't want to use this notation, but you want to use this one, here is how we write it. So the derivative of y evaluated when x is 1. And of course the answer is the same, but if we have the function, this is so much better and easier to write This requires this bar and write x equals 1. If you want to specify. If it's clear, you don't have to write it, just say, right, but I will always specify what I plugged in, so we know. Good, so then we have y minus y1 equals the slope times x minus x1, where the slope is 7. x1 is our point with coordinates 1 and 2. So then I have y minus 2 equals 7, x minus 1. I distribute. I get 7x minus 7. And then I have to add 2. So final form, y equals 7x minus 5. Okay, I'd like to talk, before we look at the exponential functions and wrap up this section, I would like to look at the velocity acceleration situation, and maybe some other couple of problems on maybe a piecewise defined function. I was very pleased. I know I didn't finish grading. I had 6, as I mentioned, 6 students that I didn't get to yet. Plus 1 file that I cannot open. I'm not sure how I hope that I can solve that problem. But almost everyone I looked at, their piecewise defined function had all the details. It was perfectly graphed, perfectly presented. You made some errors on domain and range a little bit, but not everyone. But I was very pleased with the work. You definitely understood how to graph a piecewise defined function, and I am grateful for that. Okay, so let's look at a situation.
I have a quick question.
Yes, please. Anything.
When I went to go look at the grades, it said that my file was missing for my quiz.
It says that for everyone, but I already have a grade because I graded yours. So I created another, very good question. So I created another assignment because I'm going to delete this one, but I don't want to delete the files that are there. So where you put in the file, it has 0, but then I created another column with another list of grades where the grades are entered as test 1 out of 100. Is that okay? Yeah? Yes? Okay, very good. Let me know if there are any discrepancies at any point in time. If you feel that there is something that is not right, you may be correct, I may be wrong. I'll apologize and correct it. Okay, so we are given the motion particle s of t. This is given to us as t cubed minus 3t. S is measured in meters, and t in seconds. And we're asked to find the velocity and acceleration. So let's discuss that. So number 1, part A, find the velocity and the acceleration. Okay, so first of all, we know that the velocity represents the derivative of the distance. So the rate of change of distance with respect to time is the velocity. So all I have to do is differentiate the distance formula or the distance function, and I get 3t squared minus 3. So the first derivative of the distance is the velocity. Now, the acceleration is definitely the rate of change of velocity, so it will be v prime of t, but it's the same with the second derivative of the distance function. So all I have to do is just differentiate, and I get 6t. I didn't mention, and I want to mention now. Any constant. Maybe I shouldn't use A because it looks like acceleration. So let me use C, standing for constant. So C prime, the rate of change of any constant, since it's not changing in any way, shape, or form, that will be 0. If we have a constant, we want to differentiate, like I differentiate 3, I have to get 0. In part B, after we determine the velocity and the acceleration, in part B, they want us to find the acceleration after 2 seconds. Find the acceleration after 2 seconds. That's not a problem. It's 6 times 2, which is 12. I need to write the measurement unit. So if the distance is measured in meters and the velocity must be measured in meters per second, the acceleration is a rate of change of velocity with respect to time. So the velocity is at the top and time in the denominator. So that's why the measurement unit for the acceleration will be meters per second squared. So this is 12 meters per second squared. S squared or SEC, whatever you want to use. We are also asked in part C, find the acceleration when the velocity is 0. Find the acceleration. Oops. When velocity of time is 0. Well, I have to find t first. So I look at, I find the velocity function. I replace it in this equation by 3t squared minus 3 equals 0. Of course, I will divide both sides by 3 to make my life easier. So I get t squared minus 1. I move 1 to the other side. And of course, I'll take the square root, or you can factor, and I get 2 solutions. T equals 1 second, or t equals -1 seconds. Algebraically, both solutions are correct. However, this makes no sense. So we found that at time equals 1 second, the velocity is 0. And now we are asked to find the acceleration. So here, A of 1 is 6 meters per second squared.
Going back to part A, how did you get 6 as the second derivative of t?
I bring 2 in front. I have to multiply it by 3 because this becomes a factor. 3 times 2 is 6, and I get 6t. When I differentiate the constant, I get 0.
Gotcha. All right, thank you.
Better?
Yes.
Okay, perfect. Okay, we have multiple applications here, but there is at least 1 or 2 other that I would like to go through because you will see them again later.